Kerstin Dautenhahn, and she's going to talk to us about towards adaptive social robots. So this is another project in the AI for social good, integrating physiological adaptation in human-robot interaction, which is part of her expertise. So Kerstin Dautenhahn is a Canada 150 research chair in intelligent robotics. She has a joint appointment with the Department of Electrical and Computer Engineering and System Design Engineering, and is cross-appointed with the David Cheriton School of Computer Science at the University of Waterloo. She's the director of Social and Intelligent Robotics Research Lab. She's the editor-in-chief, jointly with Professor Angelo Cangelosi, University of Manchester, of the journal Interaction Studies, Social Behavior and Communication in Biological and Artificial Systems. So Kerstin, please entertain us with your talk.
Thank you. Let me share my screen. So yeah, thank you for the introduction. So here in Waterloo, as you've heard, I'm the director of the Social and Intelligent Robotics Research Lab. We are interested in many topics regarding social robotics and human-robot interaction, in particular also with regards to using AI approaches. So this research can range, for example, from cognitive robotics, where we are interested in what could be suitable AI architectures for such robots that need to interact with robots, to developmental robotics. That is an area where people basically try to take inspiration from how children, for example, learn new skills, learn language, and then try to emulate that on a robot. But I'm also very interested in application areas, so developing robots that can be beneficial, that can be assistants, that can be coaches, or that can be tutors. So I'm assuming that not all of you are very familiar what I actually mean when I say social robot. So some of the definitions that are being used are pointing out that social robots are robots that are specifically designed to interact with people in human-centric terms and to operate in human environments alongside people. So we are not talking about robots that are completely separate from humans. So, for example, when robots were first introduced in an industrial context, they were typically put behind cages. So people did not have any direct contact with them. No one actually worked alongside with them. But this is different from the kind of social robots I'm talking about, which are robots that are meant to work and share the same space as people. This can be in workplaces, this can be in office environments, it can be in hospitals or in therapy centers or in care homes. And as you can imagine, that involves quite a lot of robotics, AI, challenges. So what is really special about these social robots is that they engage with people in an interpersonal manner. They do not treat people just as another object that they need to deal with in their environment. They have skills to communicate and coordinate their behavior with humans through verbal behavior, so speech, non-verbal behavior. This can be gestures, facial expressions, for example, or affective modalities, so communication via emotion. So this is just a little introduction on what social robots actually are. The social skills that these robots have can vary widely. And in some cases, you might not even need any social skills. So let's say you have robots operating in very remote areas where they are spatially and sometimes even temporally separated from the human operators. Right now, for example, on Mars, we have Percy, the Perseverance Mars rover. Clearly, it doesn't need to be trained to use gestures or to recognize facial expressions. That would just be pointless. But this is this situation is very different when you talk about robots sharing a space. So robots, for example, working alongside maybe search and rescue teams in disaster areas, or could also be in a firefighting scenario, as you've heard from Professor Crowley, or agriculture environment. They need even more skills when they actually move in with people, when they, for example, share their home with people, or an office environment, or if they operate in a hotel or as a tour guide in a museum. And at the other end of the spectrum, these skills are not only desirable and will improve the robot's functioning, but they could be key. So if you talk about robots that should be used in rehabilitation or in therapy or in nursing care, then the fact that they need to behave socially in an acceptable manner becomes key to their actual use, because otherwise people would just not use them. And in some applications, for example, for more than 20 years, I've worked in robot-assisted therapy for children with autism, where the main function of the robot was actually to teach children about communication and interaction, which means that these robots needed a very high level of social skills. And the same also applies for other application areas people are discussing these days, for example, robots as companions, even in people's own homes or in care homes. So when deciding how social these robots should be, you need to consider various dimensions. I just very roughly indicated. So as already explained, you need to first decide, do they actually have any contacts with human, remotely or in person? What is the robot's functionality? Is it just a very limited functionality? For example, we have the Roomba robot, the vacuum cleaning robot that many people have in their house. It doesn't have particular social skills because it doesn't need it. It has very specific, well, one actually very important functionality. It should clean the floor. And although people maybe might view it as a creature, it has not been designed specifically in order to be a social robot. You also need to consider what role should this robot play in your particular application. Is it just meant to be a tool, similar to other tools that people are using, or is it actually meant to be an assistant or companion? And then finally, you need to consider how important are these social skills. As I mentioned, is it just an interesting add-on, or is it fundamental to the robot's role? So when I talk about companion robots, that's usually being used to describe robots that first of all have certain tasks, so they can make themselves useful. They're not just robots who stand around and look interesting and sing songs or do dances. No, they need to have a certain job, so to speak. But they need to carry out these jobs in a social way, in a socially acceptable manner, which then requires these social skills that I mentioned to you earlier today. And key for developing robots, in particular in applications, is a dedicated human-centered approach where you go through different iterations of prototyping, co-design, so where together with your potential users and anyone else involved in the deployment of such system, you are jointly designing a system, and then you go through experimental testing with users, then you go through various iterations of that. So it is a highly iterative process. Normally, these are being done in-person experiments since March last year. Of course, it has been proven difficult, so a lot of our co-design has moved remotely. These robots, these social robots, come in different shapes and sizes, as you can see here. This is a partial family photo of the robots we have in the SIRRL lab. So some are clearly humanoid. with different types of designs. So some are more futuristic, like the robot you can see right in the middle. If you can see my cursor here, I'm not sure if you can see it. Other have a more cartoon-like appearance, like this one here. It actually has a screen. It's the cutie robot. You will hear about it later in my talk. It can also show facial expressions, but it's also a screen you can use for any other displays of information. And this is the Pepper robot, which has been used now extensively, not only in basic research, but also in application areas in hospitals or shopping malls, for example. But other robots are more zoomorphic. So this robot here, the mirror robot, it doesn't imitate any particular animal. Some people say it's a mixture between a dog and a rabbit, but there's certain advantages using zoomorphic robots as opposed to humanoid ones. As soon as you use humanoid robots, and here's the final one, the fur-head robot, which is basically just a robot head that has different expressions, can also have different personalities. The problem is if you expose people to a humanoid robot, they will automatically have very high expectations. They will assume the robot does not only look like a social robot, but that it can perfectly understand language. It has general artificial intelligence, so it basically knows similar things to what humans know. And so depending on the application area, it's sometimes beneficial to use robots that don't look anything like a human being, robots that just look machine-like, or as in this case, animal-like. So developing these companion robots, as I mentioned, using body movements, gestures, facial expressions, using language, is scientifically challenging and exciting, but also expensive. So why do we need companion robots? And there are indeed several application areas where currently worldwide many research groups are working on. There are first of all people with special needs who can greatly benefit from assistive technology. There's already a lot of other assistive technology that many of them are using, so robots could definitely contribute to this particular application. And why it's important for society, we know disability creates an education gap and a wage gap, and it greatly impacts, therefore, on unemployment, but also poverty. So any contribution to elevating some of these difficulties would be a great goal to have. Other research is looking at robotic co-workers, or so-called cobots, with the vision that in the future, the next disruptive trend will be about personalization, where in industry, people will work alongside robots that can cooperate with humans, and where human intelligence is complementing the skills that the robots have. And the third application area I just want to hint at is addressing an aging populations. In Canada, but also in many other countries, we have an aging population with very significant healthcare costs involved, also including a lot of work of family caregivers, which often have to shoulder a lot of this care work. So again, any contribution that could be done would benefit the Canadian healthcare system, but also benefit people who take care of their loved ones. The goal in neither of these application areas, at least for me, is to replace any humans. It is really this idea that in this case, human carers and robots would work hand in hand and complement each other. So robots could also be used very efficiently to support healthy aging. So to support people to live independently in their own homes as long as possible. So, for example, the type of assistance they could provide in a care home or in someone's private home is physical assistance. let's say someone is already is still very healthy, but maybe has developed some mobility issues, then the robot could, for example, be used for fetch and carry tasks, to fetch objects from a higher shelf or to pick them up from the floor. Robots could provide cognitive assistance, for example, reminding people to take medicine or to go to a doctor's appointment. And they can be used as coaches to teach about exercise or nutrition or hygiene. This is, for example, one of the assistance robots, home companion robots, that we've used in some of the research that I've been involved in. So in all of these application areas, potential application areas that I've just mentioned, robots need to be socially intelligent. They need to be able to learn and adapt in real time to the users, because these are very complex and dynamic environments. You cannot pre-program any or script any of the behaviors. They also need to be able to provide encouragement and assistance to people in all of these application areas, with the goal to influence when it comes to healthcare specifically, and healthy living, positive and healthy behaviors in the users. But a key research challenge here is, how do we ensure a high level of engagement from the user? How do we ensure that users find the robot useful, that they are not getting bored with it? And importantly, how do we improve the quality of the interaction? Because the higher the quality of the human-robot interaction is, the more we can predict people would be engaged with the robot in interactions, and the more they would accept people in the interactions. So how can you improve the quality of human-robot interaction? There could be many avenues. But one of the key challenges is that robots should not only know what people do and infer people's goals, what they might do in the future, but they should also know how people feel. So they should know about a person's internal states, vital signs, stress level, because this could be an important source for adaptation and learning for the robot. So such knowledge would allow the robot to be responsive to the person's internal states, monitor them, and provide assistance and support. So let's now focus on the concrete application of an exercise coach. So a robot that should help people to do regular exercise, but in a way that they don't over-exercise and they then, for example, get into some very unhealthy behavior. People should exercise in a desirable range. They shouldn't do too much exercise and they shouldn't do too little. So the question is, how can you encourage someone to exercise exactly in this desirable range based on a person's vital signs? Now, in this particular context, the robot could provide multimodal feedback. If, for example, they see that that the person is doing too much exercise, that its heart rate is increasing towards an unhealthy range, it could give feedback via the robot's movement, speech, facial expressions, and emotions. And the long-term goal here would be for the robot to adapt also to individual users, because each person is in a different situation. Some people exercise a lot every day for a couple of hours. Others exercise very little. It also depends on the health, on the age, on the weight, on what would this desirable level of exercise be. But ideally, so the robot should adapt to individual users and also learn from multiple interactions. And this was the motivation for the HRI PhysioLib project, which develops a software framework to support the integration of physiological adaptation in human-robot interaction. And it's this project that received generous support from the Microsoft AI for Social Good initiative. And this is my wonderful research team here at University of Waterloo, which are graduate students, but also postdocs in my team. So again, the motivation for using physiological signals in human-robot interaction, so HRI stands for human-robot interaction, is to improve the quality of the interaction, to allow the robot to reason about the affective states of the humans, the physiological states. You might say, well, why can't you use just cameras? Why do you need to use physiological data? Well, in many of those application areas that I mentioned, if you only use visual data, it is often not very reliable. The accuracy is often very low. It can suffer a lot from this real-world noise in the case of an exercise robot, or exercise coach that promotes exercise that people do. People move around. They are not always in the field of view of the camera. And of course, cameras, that has already been mentioned earlier in this session, can also raise privacy concerns. So physiologically sensitive systems have previously been used to improve user experience, and we wanted to build on this body of research. So a little bit of background on the type of work you do in psychophysiology. Let's say you are measuring a particular physiological signal, for example, heart rate. You can have a baseline. Baseline could be the resting state. You just have people maybe, sitting quietly or standing quietly without doing any exercise, and then you expose them to a particular situation that could be exercise, or when it comes to emotion, you might maybe show them emotionally, sensitive videos. You might show them funny videos. You might show them sad videos. So you have this intervention, and then you see a certain reaction. And what you can then see, and what you are interested in, is differences from the control group, the group that are not exposed to this condition, as opposed to differences of the experimental group, the comparison group. So you would observe how these signals change. And in some situations, you might not want to have a baseline, and researchers might just be interested in the just looking at the control group and the comparison group, what happens to them once you expose them to this particular situation that is called responding as opposed to reacting. So physiological sensing, some sensors that have been used is ECG, that measures the electrical activity of the heart using electrodes that are placed on the skin. EMG has also been used. It records the electrical activity produced by the skeletal muscles. And finally, electrodermal activity, which measures the neurally mediated effects on sweat glands through changes in the skin conductivity. So when people get stressed, you would see, for example, differences in their electrodermal activity that you can measure on their skin with specific sensors. So we now focus here in this project on ECG, where we measure the heart rate. And in particular, this is the blue line here shows just an example of a normal heart rate. We are measuring the distances between these peaks. It is called RRI. And in particular, we then measure the heart rate variability. And this heart rate variability that you can compute from these signals can be used to infer stress excitement, but when it comes to an exercise coach, which is what we focus on, it could also indicate exercise performance. So as I've mentioned, physiological signals are widely used already, but primarily, or in many cases, for post-experiment analysis. So you collect the data during the experiment, and then afterwards you are analyzing it. Many systems do not in real time respond and react to the person's vital signals. And they are often just used to extend the robot's feedback modalities by simply mirroring the captured human body signals. So, for example, if they would, this is also called biofeedback. So, if they sense a person is in a certain mood, or they detect a certain emotion, the robot would just imitate it, mirror it back. But there's not so much work on actually using physiological data in real time to create physiologically adaptive behaviors in a social robot. And this is exactly what this project now is about. And as I said, we focus on an exercise coach. You have a robot and a human exercising together. There have been some approaches in the literature, but typically they just focus on one particular experiment or one particular application, rather than developing a more common framework, which is our goal. And interfacing these sensors and robots can be very, very demanding, and transforming the raw physiological data to usable features also require prior knowledge in psychophysiological principles. And finally, already existing software tools are often commercial products. They require licensing, or they do not provide support for real-time adaptation. So to address these gaps in the literature, we then developed these framework. So just very briefly, on the left-hand side, you see the physiological sensing of the activities of the human. Different sensors can be interfaced here, and that is indeed our goal, that in this framework you are not limited to a particular sensor or set of sensors. You can interface a number of different sensors, so it would facilitate different types of experiments. Here you have a processing module that also does data logging, where you first of all have to process the signals, you have to extract certain features, and then you have to create, either using machine learning or heuristic rules, you need to create procedures for adaptation. Adaptation, in the sense, is that a robot, and we want to be able to interface a wide variety of robots based on different also software frameworks. ROS and YARP are very widely used middleware frameworks used in robotics. So our system will be general enough, and the robot can then use its screen or speech or facial expression, body language, lights, or any other feedback mechanism in order to interact with the person in an appropriate way based on the signals, based on the physiological signals that the robot in this way has been able to respond to. So we are using this particular framework here of LSL. I can't go into too many details of the details of this framework.
2 more minutes, Kerstin. 2 more minutes.
Yeah. Okay. Yeah. So we have used it with different types of psychophysiological sensors. We also explored different types of processing modules. As I said, we need to processing the signals and the adaptation. We have some heuristic processing modules, basically if-then rules. We also have probabilistic models with machine learning that we will want to investigate in future. So let me now just show you a video in order to complete this presentation. So this would be the QT Physio coach that integrates all these different processes that I've just explained. We get the signals from people about their physiological states. We have ways to extract the relevant features, and the robot will then be able to provide feedback. So here, this is an exercise coach, and this also involves people listening to music and watching videos, and the robot, you can see here on the right, then responds with appropriate verbal and non-verbal feedback in order to make sure that the person who is exercising, that the person's heart rate stays in a certain desirable area. So this is the video. It's just 1 minute, and then I would end my talk. So here the exercise starts slowly in order to incrementally bring the heart rate up. It also includes some more complex and more demanding, physically more demanding movements. The robot then also gives feedback by using gestures and voice if the heart rate exceeds, if it's outside a certain desirable range. So that's basically this system, this HRI Physiolib framework that will allow us in future also to do experiments. Once we can go back to in-person recruitment of participants, we will do experiments with participants who come to the lab to see how effective and how acceptable and how usable this system is to have this socially intelligent exercise coach robot. Thank you.
Thank you, Kerstin. Yeah, thank you for your excellent presentation. I have a question, and then there is a question from Paul Benedetti. The first one, Kerstin, is that the area of robotics has, evolved over the years. We used to have, the robotics manufacturing and these type of large robotics that we use for the industry, and now we are switching to what we call social robotics. And there is, a very big, difference between the two systems. An expert in the original robot systems is different than the knowledge of new experts in the area of social robots. For new junior faculty members or students who would like to go into this particular area, what is the major type of things that they need to learn to become, into this particular field?
Yeah, thank you. This is an excellent question. I should have mentioned that human-robot interaction in social robotics is a very interdisciplinary field. You cannot just rely on regardless of how excellent your engineering knowledge and your robotics knowledge is, you cannot solve any of these problems in this field without also learning about people, learning about human-computer interaction, being able to read articles from psychology, from health sciences, from sometimes even philosophy when you talk about ethics of social robots. So my advice would be, if a younger faculty member wants to go into that area, to not only try to educate themselves in some of these areas, but also seek contact to other people who know about those fields in order to set up collaborative projects. But I'm afraid at the end of the day, for someone who works in robotics, there's also a certain level on how you need to educate yourself. You cannot simply cut everything into different areas of domains and hope by putting together all these pieces of the cake that you would actually solve that particular problem. There has to be overlap. So psychologists, they need to educate themselves a bit about robotics. Engineers need to educate themselves a little bit about psychology. and other fields. This is at least my experience on how it works in the field.
Yeah, because I know that in a lot of the universities, I mean, they have been teaching the robotics courses for almost 25 years. I mean, the same curriculum, they haven't evolved, and we are very glad that you are with us now, that you are teaching, I mean, these type of advanced subjects, which are very important, I mean, for human-machine interaction, for real-time implementation, especially for Internet of Things nowadays, where you have wearables. So all of these are part of this ecosystem. So it's good to have all these type of courses, course in conventional type of robotics, control systems, the usual ones, but also some other type of courses in the fields of social robots, in the field of machine learning, integration with real-time systems. So this is very important in the curriculum, and it will also impact the industrial type of sector as well. Let me look at one of the questions here. So there is Paul Benedetti mentioned, I have been fascinated since Tamagotchi and Furby, such a huge area from pets to workers and companions. Some earlier presentations today covered trusting AI and predictive behavior, but I can see robot companions having certain new moral, ethical, social issues, which is the case. Will we replace friends with AIs? What are your thoughts?
No, I mean, I'm myself a firm believer in robots complementing human skills. So none of my projects works on replacing people. I'm more interested. So let's say let's make it concrete with this exercise coach. I would not want to replace human coaches, but the nice thing is if you have such a robot at home, you can use it anytime. If you wake up at 2 a.m. at night and you suddenly feel like I want to do some exercise, you just switch on the robot and it would help you doing it. You can certainly not at 2 a.m. in the morning phone your human exercise coach or go to the gym. Talking about trust, ethics, it's very, very important. In my research field, regardless of the conferences or journals, and there are many dedicated conferences and journals in those fields, there are a lot of also research studies on trust. I myself also have research projects on trust and human ethics. You need to be very, very careful in order not to create a dependency. I'm myself particularly concerned when it comes to vulnerable people. Maybe people with dementia, people with Alzheimer's, or children. Clearly, you need to be very, very careful here. And as a researcher, you need to be very clear on what your goals are and what the robot should do and what it should not do.
Excellent. Yeah. Thank you so much, Kerstin. Thank you, Alex. Thank you, Mark, for your contribution. It has been an excellent session. And I invite you, if you would like to join the MyTax, there is a MyTax event happening now. I mean, the MyTax representative is talking about MyTax, the program with MyTax, and possibly collaboration between MyTax and the AI Institute. Thank you again for your contribution, and talk to you soon. Bye.